All right, so that was fun. This is again, this is the way it goes. So, remind you, yesterday we didn't do a whole lot. One of the last things we were talking about uh, was how to calculate or determine what the internal loads were in a particular structure. So, just again, this was in section 1.2 in the textbook. In particular, we were talking about internal loads, right? So as opposed to external loads, uh, which mostly what you dealt with in statics, these would be your applied loads, support reactions, weight, things like that. These are the forces and moments internal to the structure. And we're going to basically use the method of sections like we did with trusses in statics. And there's a very set procedure. You're basically going to follow the same steps pretty much every time. You'll see this in your textbook. It's on page 10. You'll find a much more maybe detailed, lengthy procedure. I'm going to give you my shorthand version of the steps to follow to solve one of these problems. First thing you're going to have to do would be determine any necessary or needed support reactions. So this would be the first step, sort of. I'll explain more in a second. So determine any needed support reactions. Now, if you remember anything from method of sections with the truss, we're going to cut this thing in half, and it depends on which half we're going to work with as to which of any support reactions that we'll need. So just remind you, this depends on the section that's going to be chosen. So in other words, really the first thing you do before you do any calculations is you got to make a decision. I'm going to cut this in half, and if I'm going to work with, say, the left half, then I need to find the support reactions on the left side. And I don't need the ones on the right. If I'm going to cut it in half and work with the right side, then I need to find those support reactions and not the ones on the left. All right, so that would be the first step, and you would accomplish this by applying the equilibrium equations, which remind you, everybody should know this if you made it through statics. We have three two-dimensional equilibrium equations. Some forces in x direction got to be zero. Some of the forces in the y direction got to be zero. And some of the moments about any point also got to be zero. So you'd apply those to the whole, I'll just say structure, and calculate any support reactions that you're going to need. Okay, so that would be first step. Once you've decided which half you're going to work with, you found the support reactions that you need. Next thing you're going to do is figuratively cut the structure So we're going to cut it through whichever cross section we are trying to determine the internal loads for. So cut the structure through the desired cross section. Right, so whichever cross section you were trying to calculate the internal loads, that's where you're going to cut it in half. After you do that, you're going to draw the free body diagram, again, of either section. Okay. You're going to get the same results either way, whether you work with the left side, right side, whichever half you've decided to work with. That's the half you want to draw the free body diagram for. And then finally, last step is now you're going to apply your equilibrium equations to the free body diagram of the chosen section. So whichever half you decide to work with and you do the free body diagram for, you're going to apply your equilibrium equations to that free body diagram. Again, same three equations. It doesn't matter what order you apply those in, but I'll give you a recommendation or a suggestion. Good place to start. Would be to sum the moments about the point where you cut it. Right? So sum the moments about the point where it was cut. Now, the reason and motivation for that, if you remember a little bit from yesterday, if we're looking at this cross section here, we're going to have three possible internal loads. So this is point C. So the advantage to summing the moments about where it's cut is you eliminate two of your three unknowns. Right? So if you sum the moments about C, for example, the normal force NC and the shear force VC don't cause a moment about point C. So you eliminate those two, you can sum the moments about C and you can find the moment. You'll only have one unknown in that equation. All right? All right, so any questions about the process, the procedure we're going to follow before we work a problem? Again, I'm taking silence. Is everybody's good at this point? All right, well, let's try to work a problem. All right, so we are going to try to find the internal loads acting on the cross section at point C, I think I called it. All right, so again, I know there's a little bit of lag, so I'm going to draw this picture of this beam with this loading, and I'll talk about it for a minute or so, make sure your video is caught up with this. So we have a beam with a pin support at the left end. We have a roller at the other end. That's B. And we got a couple of concentrated forces. We've got a horizontal force of 5 newtons acting to the right in B. We've got a vertical force of 10 newtons. And then we have one other loading as a distributed load. Looks like 2 newtons per meter. And we need dimensions. 2 meters from the left end to the distributed load. Distributed load is 4 meters long. This is 3 meters, and then finally 2 meters, which again, a few of you I've had in class before know typically my drawings don't always come out to scale. So I'll give that same suggestion here. Go by the numbers, not necessarily what the scale looks like. So we've got this this beam, pin support at the left end, roller at the right end, 2 concentrated forces, and then a distributed load. And we're going to try to determine what are the internal loadings at point C, or the cross section at point C. And point C is located out here in the middle of that distributed load, 3 meters from the left end of that distributed load. All right, so we've got support reactions for the pin support here. We've got horizontal, vertical forces. Why that's not focusing? It's not focusing on me. I don't know. There we go. Now we're focused again. And over here at the roller, just a vertical support reaction force. We'll call it By. So here's where the first step is to think ahead. If we're going to cut this in half and work with the left side, we need to find AX and AY. If we're going to cut it in half here at C and work with the right side, we need to find BY. Now, if one looks easier or less work, then definitely choose left or right based on which is going to be the easiest. In this case, there's really not a whole lot of difference. Since point C is right in the middle of that distributed load, it really is not going to make a whole lot of difference as far as one side being easier or shorter than the other one. So, if I have a choice and it really doesn't matter, I don't know, just out of habit, I'll probably choose to do the left side rather than the right side. But certainly if it was less work, I would go with the right side. So if we're going to choose the work with the left side, then we need to find AX and AY. So we need AX and AY. So we're going to apply our equilibrium equations to this would be to the whole beam here. Find what AX and AY are, and then when we cut it and look at the left side, we know what AX and AY are. So if we're looking at the free body diagram of this whole beam, before we go any further, we need to replace that distributed load with an equivalent resultant force. And again, this is things that you should know and have learned in statics. So if we've got a constant distributed load of 2 newtons per meter, then just in general, the resultant force is the area under the distributed load, and it acts at the centroid. Well, the area under a rectangle is just height times width, so 2 newtons per meter, it's 4 meters long. That's going to be an equivalent force of 8 newtons. Right? 4 times 2 is 8. Now, it would be at the centroid. Well, if it's a rectangle, the centroid's right in the middle. It's halfway. So this would be, if it's 4 meters wide, this would be 2 meters, and this would be 2 meters. Right? So right in the center. That's where the equivalent force for the distributed load is. So if we want to find AX, sum of forces in the x direction, they've got to be 0. So we have AX going to the right. I'm taking positive to the right. The only other force in the x direction is the 5 newtons over here, so plus 5. So AX is negative 5 newtons. Again, the negative sign just indicates directions opposite what I assumed. So I assumed it was going to the right, so that means AX is 5 newtons to the left. All right. Again, all this is just statics. Everybody should know how to do this, but it's a good place to start mechanics and materials. Gives you a good refresher in statics. Now, if we want to find AY, the best place would be to sum the moments about B. And that way we eliminate BY and we can find what AY is. And again, you got to choose a positive direction. I reckon we'll go counterclockwise as positive. So if we're summing the moments about B, the 5 newtons goes through B. BY goes through B. The 10 newtons does not. So you'd have 10 times 2. Our equivalent force from our distributed load is 8 newtons, and that's located, 3 and 2 is 5 and 2 is 7 meters away from B. And then minus AY times the length is, 11? AX goes through B, doesn't cause a moment. All right, so unless, again, if somebody sees, I wrote the wrong number down or something, you're not sure where a number came from, you got to speak up, let me know. But not seeing any or hearing any question comments, so we'll assume that's right. And I got AY to be 6.9 newtons. And that's positive. I assumed it was going up, so it's going up. All right, so now here's where we cut the beam in half. We're going to cut it through C. So we're going to cut this thing in half. And we're going to draw the free body diagram of the left side. And so here at A, we've got AX we found was 5 newtons going to the left. AY was 6.9 newtons. And it was going up. Here where we cut it at C, that's where we have our internal loadings that we're trying to determine. The force that's normal or perpendicular to the cross section will denote NC. The force that's parallel or tangent to the cross section will denote VC. And our bending moment acting on that cross section will denote with MC. Those are our 3 loads we're after. And very common mistake I see students make with this type problem where you have a distributed load. Back up here and with the whole beam, we replace that with 8 newtons, located at one point. So a lot of students will take that 8 newtons, put it at the same point down here, and it's wrong because, again, that was fine when we were calculating support reactions for the whole beam, but now we're just looking at 1/2 of the beam. So we've got to place the loading that's actually on that half of the beam. So we can't just put 8 newtons here, 4 meters from the left end. We've got to put our distributed load on there. That's 2 newtons per meter. Same as before. And where it's cut at C, this would be 3 meters. Right. So we cut through that original structure. Everything to the left of that, we got to put on there just like it was. And this is 2 meters from here to here. All right, so now we've got our free body diagram of our left section, left half of the beam. But we need to do the same thing we did up here with the whole beam. We're going to replace this with an equivalent loading. So here our distributed load, again, it's 2 newtons per meter. It's only 3 meters long now. So we're going to replace that with this equivalent force of 6 newtons. Right? 2 newtons per meter times 3 meters, you got 6 newtons. And it acts right in the center of that. So if this is 3 meters y, this is 1.5 meters, and this is 1.5 meters. So it's going to be halfway, right in the middle of the 3 meter distributed load. All right, so now we've got our free body diagram. We've got our 3 unknown internal loading, and we apply our equilibrium equations to solve for those 3. As I mentioned, you don't have to start here, but a good place to start. If you sum the moments about C, set that equal to 0. Then we've got our internal moment, MC. NC goes through point C, does not cause a moment. VC does not cause a moment. Our 6 newtons, the equivalent force for the distributed load, is causing a counterclockwise moment of 6 times 1.5. Our 5 newtons for AX, that goes through C as well. So what's causing the moment is the AY there. So we got a negative moment, 6.9 times 5. And that gives me my moment equation, my equilibrium moment equation. And it's all for MC. And I got 25.5 Newton meters. And it's positive. That's indicating it's the direction I assumed, or what I defined positive to be. It was one and the same, so that's a counterclockwise moment. All right. Now, sum the forces in the X and Y direction. And while I'm thinking about it, please, you should get in the habit of doing this when you're working the homework problems, especially on a test. Yeah. Tell me which way you're taking positive to be. Right? Don't just write down the equation and you've assumed a positive direction, but if you don't write it down when somebody else looks at it, like me, you're leaving it up to me to try to figure out what you did, and that's never good. A good engineer always communicates. So indicate which direction you're taking positive to be. So if positive is to the right, NC is to the right. The only other force is in the X direction is to the left. So it looks like NC would be 5 newtons. And I assume to the right, it's positive, that means it's going to the right. And then finally, last thing, we'll take positive up for forces in the Y direction. Right? I assumed VC was going down, so that'd be minus VC. The 6.9 goes up. The 6 newtons goes down. And I think that is all the forces in the Y direction. We got VC, our force is 6, and our support reaction there is 6.9. Solve for VC. And it looks like VC is going to come out to be positive 0.9 newtons. Which again, positive means it's going the direction I assumed. I assumed it was going down. So this force is going down. And we have found our 3 internal loadings acting on the cross section there at point C for this beam. Again, it's all statics. Hold on, I got a question. I'm in. No, the moment is dependent only on, does it want to rotate counterclockwise or clockwise? The question was, I think, if I'm reading this right, this sign here, should that be negative? Well, we took positive counterclockwise. So if you're summing the moments about C, that 6 Newton force wants to cause a counterclockwise rotation. That's what determines the sign. So it should be a positive. Let's see. Hopefully that answers the question. Everybody clear with that as far as that sign? Again, the process is going to be the same for every one of these. The loading changes, the numbers change, but the procedure doesn't. Decide we're working with left or right, get whatever support reactions you need, cut it in half, draw your free body diagram, apply your equilibrium equation. Now, one last note I'll tell you about this, and then we'll stop because we're about out of time. And that would be just make note here. The directions I assumed here, in general, it's arbitrary. You could assume those forces and moments are going the other direction, and it would not make it wrong. Your answers would still be correct. But I assume those directions specifically because of two reasons. One, you're going to see if you're working a problem in the book and you're checking your answer in the back of the book, whether it's positive or negative is based on assuming these directions. Right? So all the answers in the back of the book were obtained by assuming these directions. So just make note, answers in text are based on these assumed directions. So I'll point that out that if you had assumed it was going the other way, then you're going to get the opposite sign of what the answer in the back of the book is. Doesn't make yours wrong. Now, the reason we assume these directions is because a little bit later, when we get a little bit further over, we're gonna do something where it's going to require a sign convention, and we're going to assume that these are positive directions. So again, this is based on the sign convention that's going to be used later. So we're going to define these as positive directions. And at that point, you're going to want to assume they're in the positive direction like this. So it's just a good habit maybe to get in now, that when you encounter this later, you're already in the habit of assuming that your internal loads are in these directions, and it won't be an issue later, okay? All right, so we're out of time. Hopefully I had, we hadn't had the technical issues to start with. We were actually going to get to talk a little bit about what's called stress. This is what we'll talk about tomorrow, hopefully on time at 11 o'clock if our technology is working like it should. But we'll define what stress is, and stress determines what the material is going to do. How much it's going to deform? Is it going to break? It's based on what we call stress. Stress is based on these internal loadings. So that's why we're doing this and calculating the internal loadings, is because the stress is going to be based on these loadings. We'll define stress, start there tomorrow. But at this point, you should be able to start working on those suggested problems from section 1.2. They're going to be similar to this, so try to sit down, make yourself work through some of those before tomorrow, and then that way you'll know tomorrow if you're having any problems, or if you really do understand this process, this procedure. So before I stop recording and exit the session, any questions about anything before we depart? No questions, so I will I will exit out, and I see y'all are starting to depart. So hopefully 11 o'clock tomorrow.